Hey, first of all, hi, Professor. How you doing? So this is our uh, final break for the automate logic. Yeah, the automate logic, and we decided to do a vault, an automated vault. But in this case, the vault is just going to register a four-digit password, and then it's going to compare with a previously saved four-digit password. Okay, so we can divide these all these circuit in three stages. So first we are going to the matrix keyboard, and this is the matrix keyboard. Okay, oi, oi, oi. Okay, just let me adjust the screen. Yeah. Okay, so this is the matrix keyboard. In order to get the matrix keyboard down, I needed to implement it with 15 diodes. Uh, it's it's good to say that this is not my my creation. I saw it in YouTube, so I don't know very well how this works, but it works. And how do we can prove that this is working? Well, I put some LEDs down here, and when you press the key, for example 1, you get an binary 1 here. Yeah, so all of these push buttons are set with a diode. Some of these are with 2 and with 3. This, of course, in order to get um, the binary code. And this is just DCD to prove that the number that we have here is correct. Okay, so this is just the first part. The second part is here. This was just quite a problem because this all of these are E-type flip-flops, because this is just like the first step of the memory bank. This is the first memory bank in this vault, because we need to have two memory banks: the memory bank for a preset password and the memory bank for the password you are entering. So okay, this is the first stage. This is the memory bank for the password we are typing, and as we can see, um, these are connected. This is for the okay. You're not seeing my hand, but this flip flop that we are seeing is for the first DCD, the second for the second, and the third for the third, and so on. Okay, so all of these are connected um, to this, to the binary code we are typing. And then what happened? We face a problem right here, that how you stack in a linear form the numbers that you are typing. So I recall the Johnson's counter. So this is a Johnson's counter, but of course, if we if we want um, the Johnson counter built, uh, but us like in the past lab with three with 3D type flip flops, that will be a massive thing. So I have to search uh, an easy for this, and I encounter with the 4017 BT, that is a CMOS, and I am very excited because I never use a CMOS and I connect it well, so I think it's great. So what does this thing does? When I type a one, these things get a one, and it achieve it in the one in the Q0. The Q0 launch the clock alarm to the first D-type flip-flop I want to get. So if I type a 1 is in the first position, appears in the first position. Then when I have to just wait a little, and when it's back to preset, I'm going to type again, but this time the counter is not going to send the 1, it's going to open the Q1, and the Q1 is going to open um, the second flip flop, and so on and so on. So this is just like the very heart of the circuit, because if this was or this is not working, the whole circuit will not work. So this is the very important part. Um, so as we can see, this clock signal is connected to this, because if we got a 1 in any one of these, it's going to get a 1 and a 1. And of course, this 0 is just going to launch a 1 in order to get a 0 right there, because we want a 0 can be represented by a 0 in a binary code. So we just have to like take a snapshot and um, save the 0 for the password. Okay, and this was the second stage of all the circuit. So this is the last stage, and this was just a pain in the ass. Okay, so first we use a 74 LS 273N TTL. This is just these are just like 8 D-type flip-flops, and we use it to save the previously set password. So this is like the memory card of our vault. Then this is my analog password presetting. So you set the deep switch to the password you want, and this is like the final stage of the vault, because these are 74 LS85 and these are a 4-bit comparator. So this is what we use to compare the the password we preset and the password we typed. So as you can see, this is the A equal to B, and then when we get the equal to B, we go to an array of ANDs that conduce to a D-type flip-flop. This is very important because this is going to upload the new password. This is going to refresh the password as you type the space. Yeah, that is the key. So when you press space, this is going to refresh and it's going to say that it is correct or it is incorrect, the password you type. So okay, then we have the more or less than, and all of that are connected in an array of OR gates, and these OR gates are linked to another D-type flip-flop, and this flip-flop is like the alarm that you are not typing um, the correct password. I'm sorry, my English is not fresh. But okay, just I'm going to do the simulation. So okay, this is going to set in zeros, So this here, the password now is 1111. So let's put, I don't know why, 1, there's the 1, then it's going to 0. Now I'm going to type 2, 2, then 3, 3, and I'm going to type 0, and there's 0. So it's like that. And if we come, there, there's not going to happen anything here because I don't type the space. But when I type the space, it's going to be on the red light because this is connect all to, just a moment, all to this push button. This push button is the clock signal for everything in this circuit. For every gate, it's the clock signal. So I'm going to show you the whole. It's a massive thing, but this is it. This is my vault, and this was something I was working on, but I don't know why this is not working. But this will be the alarm of all of this. So thank you, teacher, for all you taught us in this semester, and hopefully we are going to see us around the next semester. So thank you, teacher.